All right, so before we can do anything with the program, I say we need to encode it or convert it to something we can do cryptography on, and that's an arithmetic circuit. And so here I'm going to find a very simple example where some prover wants to prove that they know a value a such that um, b minus 1 equals a squared. And that's kind of a silly example, but it's only going to take me 2 gates to write that as an arithmetic circuit. So let's see what I mean by that. If we take a and we multiply it by itself, so we'll take a multiplication gate, and so we have what we have a squared, right? And then we add 1 to it, plus 1. We have something, and presumably we want it to be b. So for example, if b is 26, 26 minus 1 is 25, and so a should be 5. But I mean, we saw previously, this kind of looks like we've seen previously, right? Like this kind of circuit. Something is not going to work for us here, actually. It's going to be the fact that we're reusing a twice here, and also this wire is equal to this wire. So when we define our arithmetic circuit, actually we won't be able to reuse the same wire for the left wire and the right wire, or reuse directly the output wire of something of a gate as the input wire of another gate. So this part will be called the wiring, and will be done much later, at a later stage. So right now I'm going to fix this, and I'm going to say that the left wire here with the right wire, both are equal to a, but that's something that we'll have to check later, or both are equal to each other rather. But that will be some wiring, and then it gives us an output here, and let's call that L1, R1, O1, and then we have L2 with a constant. It gives us the output 2, and this we want it to be equal to our public input, which is 2026, for example, or something like that, right? So let's just say public inputs, and these are private inputs, and this is a constant. And can I lower this a bit? I don't know how to do this. Yeah, that works. Okay. So what I want to do is I'm going to ignore the wiring, right? Again, I'm going to ignore the fact that L1 and R1 have to be the same for this program to work, and that O1 and L2 have to be the same. That will be done much later. This is what Plonk calls a copy constraint. So basically, you need to make sure that these are copied from one equation to the other, because we're going to turn that into equation. You're going to see. But yeah, just keep that in mind. So let's write that as a series of equations. And we actually need 2 equations because we have 2 gates. In the first case, we have L1 times R1 equals O1. Or you can write that as L1 times R1 minus O1 equals 0. It's the same thing. In the second equation, we have L2 plus 1 minus O2 equals 0. And of course, I'll write here the copy constraints that I talked about, and that we're going to ignore for now is that L1 equals R1 and that O1 is equals to L2. These are the copy constraints. And here what we created is what we call constraint system. So a constraint system is really just a bunch of equations that constrain some of these values, right? So it constrains some of these values because they have to be equal to 0 eventually, and maybe some of these things are constants or they are fixed by the verifier as public input or something like that. So to do this, actually, this is a great step, right? We encoded our circuit into our program into an arithmetic circuit, and now we have equations so that we're going to be able to do cryptography on them. So that's pretty great. There's one more step we want to take though, with these equations, and it's to kind of normalize them. I don't know if normalize is the right word, but make them kind of all the same before we're able to transform all of that into polynomials, which is, if you remember, something we need to do to use our backend, our proof system. So Plonk has a type of equation that's supposed to represent all the gates that you can use, and they write it like this. So let me show you. They do L, Li, for in the first one is L1, in the second equation is L2, whatever, but in the IF equation is Li times QLi plus, and I'll tell you what this QLi is after, don't worry, plus the right wire times QRi plus the output wire times QOI. Whoop, I'm missing some I here. Plus, we're going to have a constant thing, and plus a multiplication gate. Well, let me write it like this: Li times Ri times QMI. Okay, this is kind of weird, but basically, these are, oops, what am I doing? This thing here are the left and right wires, the output wire, right? So the output wire here. Then we have the constant that is going to be helpful for this part here in the circuit, or this in the equation. And then we have the multiplication thing here, the multiplication we can have in our equation here. And what I'm saying is that with these, what I'll call selector values, all these Q's, by setting them to 1 or 0, I can toggle on and off the different wires, or even like the multiplication gate. And by setting them on and off, I can pretty much recreate these equations here. So let me show you that. For example, in the first equation, so I'm going to have two equations here, right? This is 1, this is 2. In the first equation, I have the left wire. The left wire is used only in the multiplication. So we have a multiplication. So we'll set QM here to 1, right? And the prover wants to prove that, for example, they know a value 5 such that it's the square plus 1 is equal to 26. So we're going to fill in the blanks here, and we're going to say that the left wire is equal to 5 and the right wire is equals to 5. And so here we'll have 5 times 5s. And all of that is equal to 0, right? That's important not to miss this part. We don't use a constant in the first equation, so we're going to set the constant to 0. And the output of the first equation is supposed to be equal to 25, but here, since we put it on the left, it's going to be equal to minus 25. So since we use the output wire in the first equation, I believe we almost always use the output wire. We're going to set that to 1, this Q value, right? So you understand, right? By setting these Q values to 1 or to 0, right? 1 or 0, we toggle them on and off in this specific equation. And here we actually don't use any addition here, so we're going to set that to 0 here and to 0 here. In the second equation, let me add the plus here, so it's going to be clear. In the second equation, we actually don't use a multiplication, right? So we're going to set that to 0. There's no multiplication here, there's just an addition here. And because there is an addition with the left wire, we're actually going to set the left wire to 1. And actually, there's no right wire here per se. This is a constant. The right wire is a constant. So what we're going to do is that we're going to set the constant here to 1. The constant selector value is the only one that can be set to pretty much anything. All the other ones in the Plonk paper are set to 0 or 1. But this, since it's a constant, it could be like 2, 3, whatever you want it to be in the circuit. And here, the left wire here, remember, is supposed to be, the left wire here is supposed to be equal to the output here. So it's supposed to be equal to minus 25. The right wire here, we don't care, so we can say it's equal to 0, doesn't matter. We're using the outputs, and the output, remember, here is the public inputs. So we want it to be equal to 26 in our example. But because we have a minus 25 here, it's kind of reversed. So what we can do is that we can also reverse the constant and just say that all of that is equal to minus 26. Just because we have a minus 25 here, we just have to keep it consistent. We could have said 24 and 1, or it doesn't really matter, but what really matters is that this value here is equal to this value here, because when we're going to do the copy constraints later, we're going to make sure that they're equal to one another. Okay, so and I almost forgot that one. Here we have to say minus 25 times 0, but you know, it's times 0 here because we're not using the multiplication, so we don't care. So we encoded our equations into the Plonk-like constraint systems of equations, and it's exactly the same. This thing here is exactly the same as this thing here, and this thing here is exactly the same as this thing here. So really, we didn't add anything, or we didn't change anything, or removed anything, you know. But what we did is that we put them in a form that's going to be helpful for us, and I'm going to explain that in the next video. But this video is only about the Plonk style constraint system.